Today on Under the Big Tree, we're going to be taking a look at the Girl Synth CGS13 Gated Comparator. Now this module is part of the Elby Designs Best of CGS Swamp panel, and there is quite a lot to it, so let's take a look. The Gated Comparator is a really interesting Serge module. It's a little hard to tell what it does by first looking at it, but it's actually a very capable CV and trigger sequencer. It's semi-random, and as a result, it's better for exploring with and stumbling across interesting musical ideas rather than trying to use it to be able to generate something that you already have in your head. Along those lines, it reminds me quite a bit of the Music Thing modular Turing machine, as well as the Clay sequencer. You'll see how the Gated Comparator has similarities to both of those two modules as we get into it. So we hear the term comparator tossed around quite a bit when we talk about modular synthesizers, but what is a comparator exactly? Well, a comparator is a device that compares two input voltages and then sends out a digital signal depending upon which one is higher. Along those lines, it's really a simple analog to digital converter. And the way that it works for our purposes is that you have a threshold value and then you have a waveform that you put into it. When the amplitude of the input waveform is higher than the threshold value, then the comparator outputs a high voltage. When it's below the threshold, then the comparator outputs no voltage. And adjusting that threshold to the right value is critical to getting a good result out of the comparator. As you'll see as we work here, the sensitivity knob is one of the most important aspects of the gated comparator in order to be able to get good musical results. Okay then, so we take a signal and we put it into our input, we adjust the sensitivity here, which is our threshold, and the result of that is that we get a comparator output here, which we can use as a gate. Hence the name Gated Comparator. But is that all there is to this? No, absolutely not. The gated comparator has a clock pulse that comes in. Every time that there's a new clock pulse, it measures and takes a look to see whether the input audio is above or below the threshold. If it's above the threshold, then it sends out a high voltage or a gate output that then goes into stage number 1. However, this whole thing here is an 8-bit shift register. You can think of this as like a bucket brigade. And at the next clock pulse, the values in each of these registers move down. So if stage 1 was high, then that will move down into stage 2. If stage 1 was low, then stage 2 will now be low. And then stage 1 will be filled with whatever the value is of the next measurement of the input signal. We can either loop all this data, or we can continuously stream new data into the audio input and react to it in the way that we've set the whole thing up. We can generate rhythms by tapping off of the individual steps of the shift register. We can also use the gated comparator as a Clay sequencer in that we have analog control voltage outputs that we can assign to each shift register. And when those registers are high, the voltages from all of the high registers are summed together and output from the mix output to be able to use for pitch information for an oscillator. We can control the input sensitivity with control voltage. There is some looping capacities here, and it also outputs a couple of additional random control voltages that we can use to be able to change pitch as well. So there's quite a lot here. So let's start a bit at a time, building our knowledge from the ground up. To use the gated comparator, you need two things. The first thing that you need is a clock input, which we are going to plug into the clock port here, and that's just a pulse output from an LFO. The other thing that you need is an analog signal for it to sample. So in this case, I'm going to use the output of an oscillator. You can see that right away it lit everything up, which means that the oscillator itself is too strong relative to the threshold. So what we want to do now is adjust the sensitivity level so that we can get something that triggers some of the time, but not all of the time. And this is the most important part of using this device. So I'm going to tweak it. There we go. Until we're right on the edge. There we go. So now you can see that sometimes when it is sampling the audio input signal, it's saying, yes, this is above the threshold, and it's outputting a high. Other times it says, no, it's below the threshold, and so it's outputting a low. And you can see that the signals themselves are moving down through the stages based on the clock pulse itself. So if I go over here and slow down the LFO, and slow down the rate at which the unit is sampling the audio input, you'll see that it is happening much more slowly. Okay, so now what do we do? Well, now let's take a look at using the gated comparator as a trigger sequencer. So what we can do is go along and look at any of these registers and use the gate output into an envelope, for example, to be able to open and close the sound of an oscillator. So let's plug into stage 1. There it is. Not very interesting, but as it turns out, if we start adjusting the frequency of the oscillator that is coming into the gated comparator, we can start getting different rhythms. So I'm just tweaking the frequency of the oscillator a little bit. And we can also change the density by adjusting the sensitivity. There we go. So now the rhythm is a little bit slower. So much of the interest of an analog system like this is that the smallest little changes to the system can really change in quite dramatic ways what it is that you're hearing. All right, well that's kind of boring. How do we make the rhythm a little more interesting? Well, what happens if we tap off of a couple of these different registers at the same time? Then we can use those to trigger different oscillators, and we can generate rhythms that counterplay between the two of them. So let's see what that sounds like. I'm going to plug into number 2. All right, that's one kind of rhythm. Let's plug into number 3. And as we tweak, and as we change it around and play with it, we can find different rhythms until we find one that we like. Okay, now here's where part of the semi-random part comes in. All of the gated outputs have an associated analog control voltage here. We can adjust these, and then the mix output is outputting the summation of all of the different stages that are lit at the same time. So let's see what that actually sounds like. I'm going to take this mix output, and I'm going to plug it in to the 1 volt per octave input of an oscillator. Now I've got that oscillator triggering on every pulse so that we don't get confused by the rhythm. All right, all of these are down, so nothing is happening right now. Let's start experimenting with changing them. And right away we start having an interesting melody happening. Now if we take the output of the oscillator and we trigger it not from every clock pulse, but from the gated comparator instead, then we start hearing just fragments of that melody coming out. So the mix output is still sending out all of that control voltage data, but we're only hearing part of it based on when the gate is actually opened, based on this output right there. Okay, let's talk a little bit about the audio signal that is going into the gated comparator. So as we established, every time there's a new clock pulse, the gated comparator samples the amplitude of what is coming into the audio input, and then comparing it against the threshold level that we've set with sensitivity, and then is using that to determine whether to output a high or a low, a 1 or a 0. So right now, if we listen to this rhythm, we can hear that it is coming out of an oscillator, which is fairly regular, and it's giving us a fairly regular rhythm. So it's semi-random and there are some changes, but it's basically a rhythm that we can recognize. Now, what happens if instead of coming out of an oscillator that is continuously repeating itself, we come out of a white noise generator, which is completely random? Well, let's give it a try. We'll plug into white noise and then we'll have to adjust the sensitivity to make it work. And let's see what happens to the rhythm. Okay. So the rhythmic pulses are really random sounding now. So this notion that noise, which is essentially random, is going in and being sampled and creating random rhythms here, rather than the rhythms that we were getting from the regularly generating oscillator, makes sense. Let's compare the two again. So here is white noise. And let's plug it back into a sine wave. So as it turns out, the gated comparator is really pretty good for doing two-part analog synthesizer counterpoint. So in addition to the mix output, which we use to be able to generate these semi-random melodies, there's also a mix inverted output right below it. And that creates an inverted version of the same thing. So let's hear what that sounds like. So we'll plug that one back in, and then what if we were to take a second oscillator and plug it in as well? Let's start by... Okay, so we have these two oscillators that are both triggering from the same rhythm. One of them is getting this mix pitch input, and the other one is just sitting on the same note because it doesn't have any pitch input. What would happen if instead we plug that input into the inverted mix? Alright, now we're getting some interesting kind of counterpoint. So to be able to really make this work though, now what we want is to have the second oscillator running off of a different set of rhythms than the first one. So let's pull it out and let's try it in number 2. And that gives us a different sound. It's still a little bit on the nose, so let's see what we can do if we can find some other outputs that might give us something that's rhythmically a little bit more interesting. There we go. Now we're starting to get something that has got a little bit of surprise and delight to it. And we can, of course, continue fooling around with our control voltage outputs for the different gates until we find something that we really like. Again, this is nothing that I would be able to generate by writing some rhythms on a piece of paper and saying, I want to do this melody or that. But it's this process of exploration and working with the machine in its semi-random mode and in this sort of person-machine dance that I like so much. Okay, there is also another set of random melody outputs on the gated comparator, and that is the random and the random inverted. The way that it works is that there's an algorithm within the circuit that takes a look at the state of the overall shift register and then sends out notes based on that. So let's hear what we have here. So we don't have any direct control over this other than how much we can adjust the density of notes that are coming into the shift register. So let's play with the sensitivity a little bit. As we dial up the density a little bit and we see more of the lights lighting up at the same time, we hear the melody changing and adding a bit to it. And just like the mix and the mix inverted, there is a random and a random inverted as well. So let's hear what the inverted sounds like at the same time. And both of them together. Now we could use these in conjunction with the mix and the mix inverted into two more oscillators and be able to actually get 4 CV sequences coming out of the gated comparator at the same time. Now, I've mentioned repeatedly how important that sensitivity knob is, the threshold knob in determining how to be able to make this thing behave musically. What I didn't mention is that there is also a CV input that we can use to alter the sensitivity as well. So this makes things even a little bit more random and tricky, but let's give it a try. Let's plug in a slow-moving triangle LFO into that input. And we get a different sound. Let's change the rate of that LFO and see how that changes things. I'm slowing it all the way down, and now I'm going to slowly speed it up. So much of this stuff is like balancing all of these things on knife edges. There's this whole journey of exploration, and you never know exactly how these different things are going to change things. We know that they will change them, we just can't predict the exact way that they will. Let's change the waveform a bit of the LFO and see if that changes anything. Lots of experimentation. It's like driving a bus from the back seat. Okay, so what we've learned so far is that this is a pretty good machine to be able to generate random melodies. But what if we wanted to constrain that randomness a little bit in terms of the melodies? Use the best parts and the most interesting parts of the gated comparator, but at the same time be able to have a little bit more control over which pitches that we are choosing for our loop. Well, the way that we can do that is by using another sequencer and have that sequencer be generating the pitches that we want and then having it being triggered by the rhythm outputs of the gated comparator. So let me show you what I mean. Let's start by plugging the gate for the oscillator directly into the pulse. All right, so now we're hearing every clock tick on that oscillator. Now what would happen if we plug the pitch input of the oscillator into the 8-stage sequencer that we have, another module here. So now we have the notes of this major scale, which are all of the notes that the gated comparator can choose from, quote unquote. So now, instead of it being on the nose where we're hearing every pulse and we're hearing that boring major scale over and over, we know that all of the pitches that it's going to get are going to be coming from that sequencer because they'll be triggering at some point or another. But now let's take the rhythms that we have from the gated comparator and see what we get. So we can hear that all of the notes are coming from that major scale, but they're happening within the rhythm that's being generated by the gated comparator. So we have got still a constrained random situation, but we have a finer control over which notes we want to be able to pick for it. I think this makes it more musically useful in a lot of ways. So now here is the same thing with our two oscillators both being triggered from that sequencer that is just generating notes of a major scale. And of course, if we want, we can use another channel out of the sequencer to be able to set a different set of constrained pitches for that second oscillator to use. Let's give that a shot. Okay, so using that same technique of generating every pulse coming out of the LFO to be able to hear what all of the notes are, we've created a little series of choices for a bass line. We will trigger that from the gated comparator again. And you can hear that because I have a lot of the tonic choices on a number of stages within the sequencer, that note is actually coming up quite frequently. So now let's bring back in the other oscillator and see what kind of a little melody we have. We can tweak the tuning a little bit to be able to make it a little bit better. This is analog land, but you get the idea. You can just keep going, tweaking all of these little parameters for hours. Okay, now we're going to talk about the final and, in my opinion, most counterintuitive part of the gated comparator, and that is the loop mode. So up to this point, we can think of it as being in streaming mode, in which it was constantly reacting to whatever the oscillator or noise input was that was coming into the input. However, now we take that away, and instead we program in a loop that it can loop through over and over again. Now, there is a semi-random aspect to this as well. It's not as easy to be able to just get a cut and dried melody as you want, but we absolutely can create something that is replicable. And in this way, it's very similar to the Turing machine. So, the first thing is that you can be either in loop mode or in streaming mode. You can't be in both at the same time. And so the first thing that you have to do is remove the audio input. So again, if you're in streaming mode, you always have to have an audio input or nothing will happen. If you're in loop mode, you can't have anything in that input or it won't work. So then if we take a look over here, we have one switch here that says manual loop. That is a 3-position switch. The down is in loop mode, middle is nothing, and up is a momentary switch that loads a bit into the top of the shift register. Up here, we have 3 other elements that we have to be concerned with. Here is the loop enable switch, which is off or on. Then there is a loop enable input and a loop in input. So in order to start, you can't loop at all without the loop enable being on. So we turn that on, we have the clock continuing to trigger, and now that the loop enable is on, we can go and click this up into the momentary position, and you will see that it inputted a high bit. Okay? But because of the fact that it comes back to the middle, it's not looping yet. So in order for it to loop, there are 2 different ways to do it. One is to click up and then quickly click it all the way down into the manual loop position like this. See? So as soon as I did it quickly, then we got our bit. If you do it fast, you can probably get a couple in. And the pitch that's coming out is once again derived from the levels of these CV control settings there. Okay, now, in order to clear a loop, all we have to do is temporarily turn off the loop enable switch. It will clear all of the bits, it will flush them out, and then you'll be emptied again. So let's create a loop really quickly. You can see it going, and then we're going to hit the loop enable off, and it flushes them out. Then we can make another one. And we can keep fooling around with it until we find a loop that we like. And if we don't like where we're going, we flush it, and we can start again. Okay, now there is an easier way to do it than that. So it's a little frustrating to have to flick this up and then flip it down in time to be able to have the manual loop engage before those bits fall off the bottom. So an easier way to do that is by using the loop in connection up here. So what we can do instead is we can take a trigger out from, say, the bottom of the gated comparator. Let's use step number 8. And then plug it into the loop in. Once we turn on loop enable, that is the same thing as having the manual loop down in that position. So now I can just click it up and leave it in the center position. And what's cooler than that is we can use this to be able to adjust the time signature of our sequence. So we can, all we have to do is move it to another position, let's say step 7, and do the same thing. Hard to tell. Let's plug it into stage 3 and do the same thing. And you can see that every time it goes here, it goes back and loops again and starts at the top. Okay, we have one more jack that we have to look at on the gated comparator, and that is the loop enabled jack. So if the loop in is a replacement for the manual loop switch being in on mode, in other words, we control the loop in by having a pulse from the comparator telling it, okay, start looping now, then the loop enable is a replacement for the manual loop enable switch right there. And it's the same thing in that if it receives a signal, then it knows to be able to enable the loop. So if we have loop enable off and we don't have anything plugged in, nothing happens at all. If we plug a jack, say channel 7, into loop enable, and then do the same thing, then the loop is triggering. So what's happening is as soon as a pulse gets down here to channel 7, it goes up here and tells loop enable, okay, turn on your loop, and then it's looping. Now let me show you one more interesting thing. So we unplug that and the loop goes away. Now, let's say that we plug it into channel 8, or to output 8, which is the same output that is telling the loop in to start. Watch what happens now. It doesn't work. And the reason it doesn't work is because clearly loop enable needs to know to turn the loop on before the reset gets back to loop in. So, strange thing that I just discovered. So, but if we turn it on anywhere else, say shift register number 5, works just fine. And while it's on, we can go and we can continue changing the loop by adding more points in by clicking the momentary switch up. And then we can drain the loop and start again. Well, that is the Girl Synth CGS13 Gated Comparator module, here being used in the Elby Designs Best of CGS Swamp panel. Thanks a lot for listening. As always, if you like what we're doing here on Under the Big Tree, please feel free to like, share, and subscribe. And for now, this is Nick, signing off.